It was March 1st of 2020. That was my last time traveling anywhere for a long time. All right. So I'll discuss big turbulence, which I'll tell you in a moment what it is, and you can feel free to ask whatever questions you like. All right. So turbulence is, as commonly understood, is about redistribution of energy in nonlinear systems with many interacting degrees. And the most familiar case is fluids, and the most familiar context is on flights on airplanes. And theoretically, the quantity of interest is usually moments of the velocity of the difference in velocities between 2 points raised to some power n. And the reason that's of interest is that it's related to transport coefficients. So most of the people who work on turbulence are engineers, and most of their problems consist of reducing turbulence, like designing the wings so that there's less turbulence, the airplane flows faster, making a pipe so that oil flows better, and so on. So what I'll be flipping slides. Do you know about this? I did some particular motion with the fingers the first time. One is this one. None of them. Oh, you're just going to try to reshare?
Yeah.
We need an engineer.
Oh, but last time we did a whole screen, it was slightly awkward.
I think you don't want to do the whole screen there. This, but then just there's like a way to do
Oh,
screen.
I think that's the same thing. Let me just do a continuous scroll.
I think no.
Yeah, this was. Okay. One of the things that I was discovered sort of by accident some 5 years ago is that turbulence isn't really confined to fluids. It's applicable to any weakly nonlinear system. You just need to have collective excitations or waves. And the problem becomes understanding the distribution of energy among the different waves. So the canonical example are waves on the ocean, or if it's windy, waves on the Great Lake that you have. And so the question for the ocean would be you'd measure the number of waves of a given wave number, and which is n of k, and then you make a plot. And so this was first done for ocean waves in the 60s. And if you make a plot, it's a power law with some particular exponent over some range of scales. And like turbulence in the case of, I mean, this is a fluid, but like the other turbulence I described previously, the homogeneous isotropic case, n of k is important in engineering applications because it determines with what speed the ocean mixes, how it heats up. It's important for plankton, and so on. But this still involves a fluid. There are other cases which have no fluid. So if you take a plasma, ions and electrons, the electrons oscillate. So those are plasma waves or Langmuir waves. So there's again waves, and you'd like to understand what n of k is, the number of waves of a given wave number. In the case of plasmas, the application that they're mostly interested in is making fusion devices, and the difficulty there is that the plasma does not like staying confined at high temperatures, and so it's believed that there may be an inverse cascade which excites some long wavelength mode, which could then confine the plasma. So that's an application there. So there are a number of other cases which, over like the last 10 or 20 years, which have measured wave turbulence. So one case is there are a number of groups that have tanks of water, and then they can excite capillary gravity waves because it's a tank. There's surface tension. You can take a sheet of metal and excite it, and it generates waves. Perhaps one of the most interesting is turbulent cascades in quantum gases. So like 20 or 30 years ago, Bose-Einstein condensates were made. But since then, the experimental abilities advanced. So instead of just forming the ground state, you can inject it at low K. Then there's a cascade, and then it gets dissipated at high K because they jump out of the trap. And one can then measure N of K versus K, and it roughly agrees with the prediction.
So this is a weak turbulence or a strong?
Weak turbulence, yeah.
Both of them. Both exactly.
So good. So this is, well, it's weak here because they made it weak to match theory. But the so for example, so it's weak as long. So in the case of the elastic plate, if the excitations aren't too big, it's weak. So in the case of waves on the ocean, if the waves are small, it's weak. If the waves are big, it's strong. And so the goal of the talk will be to understand what NK is if they're strong. So another context is heavy ion collisions. This was studied within the QCD community. They called it a non-thermal fixed point, but it's the same thing as turbulence. So that they collide heavy ions. Then there's some, so you start with a state which is highly anisotropic. And so most of the energy is concentrated at low K, then it cascades to high K. And so this is just, ignoring the quantum effects, this is just some nonlinear equations describing the energy. And so if one can observe wave turbulence. All right, so the main open question is what happens, what NK is if you're in the strong regime. So in the weak regime, the basic idea was understood 50 years ago. It's that's well understood. There are books about it. And the question is, so as you change, so you can continuously go from weak to strong. So you just make the wind stronger, the waves get bigger, and in effect, the interaction is getting stronger. And then you can no longer use the weak wave turbulence theory, and then something needs to replace it in order to make the prediction for N of K, which is most realistic cases. Yeah.
The weak case is the one where we have Kolmogorov scaling, like there is.
You don't. So Kolmogorov was already dead when all of this was done. So Kolmogorov-Zaharov scaling is what's called in. So the scaling N of K, if the interaction is weak, is called Kolmogorov-Zaharov. But it was done by Zaharov, but it's reminiscent of Kolmogorov scaling in homogeneous isotropic Navier-Stokes. That's why Kolmogorov's name is there.
But he probably is asking where is Kolmogorov problem in this?
Nowhere. So the homogeneous isotropic Navier-Stokes is the most difficult possible problem. So that one we're not discussing. So the key here is that if you think about a fluid, so the ocean, so it's still fluid, it's water, air, they're both fluids. The thing that the small parameter that came in is that the density of water is much higher than the density of air. So there's a small parameter which allows you to have small waves. So it's still Navier-Stokes because it's still water and air. But the key is it's not homogeneous because one has a much higher density than the other. So you can analytically study it.
And you're interested in the turbulence in the boundary.
That's right. Just the number of waves of a given wave number. And yeah.
Sorry, is this some generic phenomenon for any kind of wave, nonlinear wave system? You'll always have this kind of cascade.
Yeah, you just take any nonlinear system and you ask, I inject energy here, I absorb it here. How does the energy redistribute if I'm having a stationary state? So you're just constantly injecting, constantly absorbing, and then you ask, how does the energy redistribute? Or you take some initial conditions which are far from equilibrium, and then you just ask, what does the state look like? So it's just a generic phenomena. And the case which is easiest to study is in which there's no scale that's present. So like in the case of the ocean, the reason I said you observe particular power, NK is K to the -4 over some range of scales, it's because you pick that range of scales so that it's a range over which no other scales are present, so that everything is scale invariant. Because if other scales are dominant, then it won't be scale invariant. So the first half of the talk, I'll describe some results. In the second half, I'll show that in terms of calculations, what we're doing is just quantum field theory, but not in the vacuum or the thermal state. It's just quantum field theory in the state with occupation number nk. So it's just a modification of usual quantum field theory. Questions, comments? The key equation that goes in is, so let me remind you about the quantum Boltzmann equation. So the quantum Boltzmann equation, I guess you learn in kinetic theory or in cosmology. So it tells you the number of particles of momentum P1, how it changes. So it can either increase or decrease. It increases if particles of momentum P3 and P4 collide. And so that's this term. So it's weighted by N3 and 4. And this is the Bose enhancement factor. Then they form particle P1. And then the reverse process can happen. You can lose a particle of momentum P1, which is that factor. So this is the quantum Boltzmann equation, and it has two limits. So if you take the limit in which n is much less than 1, then you can drop these two terms and you get n3 and 4 minus n1 and 2, which is the classical Boltzmann equation for particles. And the other limit is when the occupation numbers are much greater than 1, and then you can sort of drop the 1 relative to n, and then that gives you the classical wave kinetic equation. So the classical Boltzmann equation is probably more familiar, but the other limit of the quantum Boltzmann equation is just the wave kinetic equation, which is the one we'll be studying because we're interested in interactions of waves rather than interactions of particles.
So strictly speaking, there's nothing quantum, right? But
No.
You call it quantum, but
Well, this equation is the quantum Boltzmann equation for bosons. The reason I used this equation to get to the classical wave kinetic equation is because the audience is.
oh, I see, but they're the same. Okay.
Yeah.
And remind me, why are there no cubic terms in this?
It's just 2 to 2 scattering.
It's just an assumption that that's the only scattering process. It's allowed.
You want 2 to 1, like particle creation? Yeah, I just just take 2.
You can just write this psi to the 4 theory.
Yeah, I'll write it next slide. So there are many classical interacting waves that can have a cubic contraction as opposed to quartic. I'll consider the quartic case because that's the one in which I can take a large n limit. That will be the. So in the context of ocean, surface gravity waves, it turns out they have a quartic contraction, whereas capillary waves have a cubic contraction. So yeah, in some cases they're cubic simple. So the thing that Zaharov showed, and is the hallmark of wave turbulence theory. So the thing you learn in statistical mechanics. So the question that's asked is, what are the late time? What happens to the state at late times? And the answer is at late times it should turn to the stationary state. And so to find the stationary state, you usually just set this equal to 0. That's what you do in statistical mechanics. And if you set this equal to 0, you get the Bose-Einstein or thermal distribution. So the key result is that that's not the only solution you can get if you allow yourself to change boundary conditions. So if you put in pumping and dissipation at k equals 0 and k equals infinity, you can find another solution, which is not it doesn't manifestly make the right-hand side 0, but it makes, but it does make it 0. And this is the Kolmogorov-Zaharov solution. So nk is the power law k to the minus gamma. And you can check that if you plug in k to the minus gamma with a particular gamma into this equation, then it vanishes. So it's another stationary solution. And it's the one that's physically relevant if you're pumping and dissipating, like what happened if the wind is blowing. That's the pumping of energy. Good. And these solutions carry constant flux, where this is the definition of flux. So it's just the number of waves per unit time that's passing through them. So if we're expanding our knowledge of backgrounds in which we do quantum field theory, the first case is the vacuum. the next simplest case is a thermal state. And now if you want to study systems that are far from equilibrium, the next simplest case is to have a far from equilibrium state, which this is, but one that's stationary. And so that's why we're studying this. So logically, it's the next simplest state. It's stationary, but it's far from equilibrium because k to the minus gamma is very far from the thermal distribution. Yes.
Is there a reason I should expect this kind of power law a priori, or is there's some scale invariance in this,
Good. So the reason you expect that the answer is scale invariant is because we take n much greater than 1, so 1 drops out, so the problem is scale invariant. The particular power I'll show you, it's just 2 lines to derive, it's just dimensional analysis. So to emphasize again, if you take, there's like dozens of weakly nonlinear systems that are considered. If you take any of these systems and change the boundary conditions so that you're sending flux in, then Kolmogorov-Zaharov weak turbulence theory tells you what nk you'll expect, the number of waves for a given wave number. But it only works as long as the interaction is weakly nonlinear.
Sorry, what does weakly nonlinear mean? Does it just
It means the coupling constant is so here. So if our system is the nonlinear Schrodinger equation, so it's just a complex scalar with a quartic interaction, non-relativistic. So weakly nonlinear just means it's weakly coupled, so lambda is small. Lambda is not dimensionless. So lambda small actually means lambda times some power of k is what's small. You could say the ratio of the nonlinear term to the linear term. So so for the large community of people who work on turbulence, since most cases are not weakly nonlinear, they're not weak wave turbulence, they're strong turbulence, they need something to match to. And there was, in the astrophysics community, there was an influential paper in the 90s by Goldrick and Schredhar, which is called critical balance theory. And the idea was the following. They just said, so imagine an inverse cascade. So you're pumping in the UV and the cascade is going into the IR. And so the nonlinearity keeps growing as you go into the IR. So it's a relevant operator in the state. And the hypothesis was at some point, the nonlinear term will become of order the linear term. So they're going to fix the state such that the state is going to turn it into whatever it needs to be so that the nonlinearity stops growing. So that the nonlinear term is roughly of order the linear term. So you just take the ratio of these two terms, psi to the 4th to del psi squared. So we're in a state in which occupation numbers are nk. So psi squared are replaced by nk. And so this tells you that nk should be k to the 2 minus d. So this is what they call critical balance scaling. So it's some guess of what might happen in strong turbulence, but it's not an actual theory. And in some contexts it works and sometimes it doesn't. So a similar thing was done by Phillips in the 50s for surface gravity waves in the ocean. Similar kind of argument for a prediction for what will happen if the wind is strong. So one thing that we'll see is that in the context of nonlinear Schrodinger, by doing large n, we'll derive critical balance scale.
So here the reason there's no quadratic term is sort of trying to emulate the situation where lambda is much bigger than the quadratic term.
I mean the psi squared term?
Yeah, so the psi squared term.
There's no psi squared term because there's just no psi. Why is there no psi squared term?
Does it matter?
Psi squared term would just it does, you can add a psi squared, it doesn't matter. So the dispersion relation omega k is k squared. It would just add a constant, but it makes no difference for it wouldn't change anything. So you can add a psi squared, it doesn't matter.
I see. It's not like lambda is much bigger than the coefficient.
No, you can add a psi squared, it just doesn't matter. It wouldn't change the result for n of k. So let me actually get to the answer. So we're going to as I said at the beginning, the goal will be to find n of k at when the coupling is large, which translates into low k. And so we'll do this in two ways. The first will be theoretically so we'll change nonlinear Schrodinger, and instead of one field, we'll make n fields, and then get the answer theoretically. And the second way will be by direct numerical simulation of the original equation. And surprisingly, the answers will essentially match. So let me tell you what the answer is. So in the regime of weak turbulence, which is large K, in this case, this is the Kolmogorov-Zaharov scaling. It's some power. It depends on the flux and the coupling. So you increase the flux, and then K gets larger, which is intuitively obvious, because if you're pumping in more energy, of course, the number of waves goes up. So in the strong turbulence regime, we find two different answers depending on the sign of lambda. So if we go back, so in nonlinear Schrodinger, there's lambda, and it can have two signs. It could be either positive or negative. So in high energy, one is used to positive couplings to make the system stable, which is fine. But in this case, for many systems, the coupling is actually negative. So that's referred to in the optics community as the focusing case. So the case of negative coupling is the focusing case, and it has collapses because it's negative coupling and it's unstable, but it describes many things. So for instance, for plasmas, the interaction between Langmuir waves and ion acoustic waves is, in certain contexts that are nearly stationary, is described by a nonlinear Schrodinger equation with negative coupling. So the negative coupling case is physical, and that's the focusing case. So the answer for NK depends on the sign of the coupling. So even though for weak wave turbulence is insensitive to the sign, that effect goes away as you go to low K, which is physically clear because focusing and defocusing are very different. In one case, there are collapses, in the other case, there aren't. And the result that we get is the following. So in the focusing case, the answer for NK, so it's a different power, so it just goes into a constant. This is in 2D, and it's independent of the flux. So you increase the flux. So at high K, the number of waves increases, but at low K, the number of waves does not change, which sounds counterintuitive, but that's the answer. Which is what you would expect from critical balance scaling. That NK is such that the nonlinearity is simply of order 1. So you can keep increasing the flux. It doesn't change the answer at low K. So that's what this plot shows. You increase Q, it doesn't change the answer at low K.
In this case, why is there's some assumption here of spatial homogeneity?
Yes.
Why in the focusing case, if the interactions are attractive, why
It's
is there
still-
some phenomenon like spatial collapse of?
Yeah, there are collapses, but it's still statistically homogeneous. One would still expect it statistically homogeneous. So there are many collapses, but they're spread out, so statistically. So even without collapses, if you zoomed in on a box of gas or a fluid, it doesn't look homogeneous on small scales. It's just on large scales. There's always an assumed averaging over something. So all of these are statistical quantities like NK, so you average over something. So then in the experiments, they average over time, or you average over space, or you add some, or in the numerical simulations, the forcing is not, it's stochastic forcing. So it's not a deterministic forcing, it's a stochastic forcing, which is one way of imitating some sort of averaging. If you don't average over anything, then the answers are meaningless because the system is turbulent and chaotic. So I think it's predictable. In the other case, in the defocusing case, the coupling drops out, which I'll describe shortly. So this is why I wrote that universality emerges in strong turbulence. In one case, it's independent of the flux, and then in the other case, it's independent of the coupling. So let me show you how we got this answer for large N. So this kinetic equation, the standard wave kinetic equation, which is the Boltzmann equation that everyone uses, it's just the leading term in a perturbative expansion. The right-hand side here is essentially just a 4-point function of just 2-to-2 wave scattering. And one reasonably expects that you can just compute this 2-to-2 scattering to higher order in lambda and get a perturbation series. So this is just lambda squared. So if you keep computing, you'll get a term that has lambda cubed, more n's, and so on. And these higher order diagrams you can interpret as interactions with fluctuations in the background turbulent state. So obviously we can't sum all the diagrams, so we're going to do the large N limit. So I'm going to replace the nonlinear Schrodinger equation with a large n version. So I'll make psi a vector and then take the large n version. So now my question is, for this Hamiltonian, what's n of k, both at small k and at large k? So in the next slide, I'll write down the kinetic equation. So this was actually done by Bob Kreiknen in 67. As one works on turbulence, one discovers that Kreiknen did everything many decades before it was done in either high energy or condensed matter. So in addition to solving this large n model, which I believe was before large n existed, he also solved the SYK model in 1959, a classical version of the SYK model. He called it the random coupling model. By solved, I mean he wrote down the Schwinger-Dyson equation. It's essentially the same as the Schwinger-Dyson equation for fermions. So since it's large n, the answer, so as I'll describe in the next part, in the second half of the talk, to do the calculation, one goes on the Keldysh contour and so on, but roughly the answer is intuitively clear. Since it's large n, we're summing bubble diagrams. So we're computing a 4-point function in this large n nonlinear Schrodinger equation. So we sum bubble diagrams. So the answer is a geometric sum. So the renormalized, their effective interaction is lambda over 1 minus L, where L is the value for each one of the loops. So if you were just doing zero temperature quantum field theory, L would just be 2 propagators. Here, since it's in this state, it's on the Keldysh contour. So one of the propagators is a Keldysh propagator and the other one is a retarded propagator. So the Keldysh propagator encodes the state. So that's what gives the factor of NQ. And the retarded propagator is this one. So it depends on the external momenta and the internal momentum running in the loop. Good. So the remarkable property of large n is that the kinetic equation looks just like the tree-level kinetic equation, but with a renormalized interaction, this capital lambda, which is state dependent because it depends on n. So here I wrote again, so the renormalized interaction depends on the momentum of all the 4 waves that are being scattered and on the state in a highly non-trivial way. So this is like the novelty relative to large n in the vacuum, that here the state enters into the renormalized interaction. So it's non-trivial to read off how lambda scales with momentum because it depends on the state. Questions, comments?
When you say it depends on the state, you mean the steady state.
It depends on NQ, which is what we're trying to find. Yeah, that's what I mean by depends on the state. So in other words, we have a kinetic equation, which is the one I wrote down. dN dt is blah, 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 the 2-to-2 wave scattering. But for the interaction, instead of putting a constant lambda, you should replace it with this capital lambda, which in itself depends on n. So now finding the stationary solutions becomes a much harder problem. So this is so this is the result that we find for the renormalized interaction. So in the defocusing case, the positive coupling case, at low k, lambda scales like k squared, and in the case of negative lambda at low k, the renormalized interaction scales like k to the minus 2. So this interaction is highly relevant in the wave turbulent state. So that's why it goes from being a constant to going like k squared and k to the minus 2. So here on the left is the sketch that I showed you before, which is the answer we get for, and once we know the renormalized interaction at low k, from that it's simple to derive what nk should behave like, and this is the answer one gets that I explained earlier. So on the left is the sketch that I showed before. So this is the behavior in the weak wave turbulence regime. This is the behavior at strong turbulence for negative coupling and positive coupling. And here's the direct numerical simulation, which is for only one field, but it gives qualitatively and essentially quantitatively the same answer as infinite n, which is the one we can do analytically.
What is this kink up at the top?
The kink up at the top. So in the defocusing case, one starts forming a condensate. So the cascade is from high k to low k, and then the defocusing case, one starts forming a condensate at low k. So to kill off the condensate, one has to put in fairly strong dissipation here to kill off the condensate, so that's what you're seeing with the kink. And only then do you see this power law of 8/3, which is what large N predicts. In the focusing case, one doesn't have such a problem. In the focusing case, there are collapses. So you're pumping in at high K, it's cascading to low K. At low K, there are collapses because the nonlinearity is strong, and then that just moves in some non-local way all the energy back to high K. So at low K, you don't even, so in the focusing case, you don't even need to put dissipation at low K like you normally need to. Collapses take care of it. So it's some closed cycle of just, there's a cascade which heuristically is set to be local in K space, the turbulent cascade. It gets to low K, there are collapses, and it moves back to high K. So somewhat remarkably, we don't and don't need to understand any of this to get the answer for N of K, because we're just solving the large N equation without knowing anything about collapses or so on. So any other questions? So if we look at this equation and ask, so I want to briefly comment how we got this answer. So if you look at this equation, so if you're at weak, so if the coupling is weak, then you would say I can just drop L here, because L goes like lambda, that's the loop integral. And so you just keep the one, and then the renormalized interaction is just the bare interaction, and you get back to standard equation. Now you would say, okay, I'm going to go to strong nonlinearity. I want to make lambda large or go to low K, they're the same thing. Then you would say, okay, let me drop the one. That seems like the reasonable thing to do. And that's the correct answer in the defocusing case for positive lambda. It's correct to drop the one, keep the L, and then this is the answer you get. The capital lambda scales like K squared. But in the focusing case of negative lambda, that can no longer be the answer, because you need to get a different answer for negative lambda than the one for positive lambda. They're physically completely different. And so for negative lambda, it was a bit unclear what we should do in order to get the behavior at low K. Any suggestions?
I have a question again.
Yeah.
So I guess it's for lambda. For one of these cases, I guess you're saying you get back the expectation, this heuristic that you mentioned, the n k to the d-2. That's this.
That's right. That's the focusing case, which is the one.
I see.
Yeah. So let me back. So we produce a kinetic equation, which is the one I wrote, which has this renormalized interaction. But if you just look at the kinetic equation and you ask what's the stationary solution, you look at it, you don't know. It's an integral equation. You can't just solve it. Like even if you try to write code to solve it, it's non-trivial. And you would think that analytically it should be trivial. And there's one trivial answer for what you get for strong coupling, which is drop the one here. But the second answer seems somewhat non-trivial, because that option you can't use for both signs of lambda, of what you should get for strong coupling. So the thing we did is the following. So we're going to assume, let me actually go back to the slide. So what we're going to do is we're going to assume that L takes the form of 1 plus some number times K squared. The reason for that assumption is because this L seems to be analytic in omega, which in the frequency which goes like K squared. And so it seems self-consistent to assume, or somewhat consistent to assume, that we just reach a stage where L goes like 1 plus some number times K squared. And if we do that, so if you plug in 1 plus K squared, then you get that the renormalized interaction capital lambda goes like K to the -2. So that's the answer we got. So perhaps stated differently, the issue is that if you, unless you do something special like what we did of taking L to be close to 1, you're going to get the same result that you got for positive lambda, that capital lambda gets very small at low K. Because if you drop this term, then you just have this lambda, so it's getting small at low K.
Is that one something you can compute? The fact that leading behavior is 1. I mean, the fact that it's subleading behavior is K squared. You're just saying it's analytic or something.
Yeah, that's right.
But
The one is so. So what we do is we assume that NK is such that L becomes 1 plus some number times K squared. then we plug that in, then we find the N of K so that we have a stationary solution. And then that N of K is lambda inverse. And with that N of K, you get that L is 1.
Let me skip this piece.
All right, so to make an analogy, so we, depending on if lambda is positive or negative, in effect, we get two cases, one in which the renormalized interaction grows with scale, and the other case in which it decays with scale. So this is analogous to QED and QCD. But in these cases, it's quantum vacuum fluctuations, which are leading to renormalization. Whereas in our case, the renormalization is as a result of statistical fluctuations. So of interactions between the two waves we're scattering and the waves in the turbulent bath. So here I have another picture here. So we're scattering 2 to 2 waves, and the interaction of the Hamiltonian is just lambda, but because we're in this background of many waves in a turbulent state, that interaction gets renormalized, and depending on the sign of lambda, it either gets weaker or less weak. So the negative lambda case is like QED. The positive lambda case is like QED, and the negative lambda case is like QCD. So just taking the coupling to be negative is actually a trivial way of getting So if you just took this for lambda phi to the 4th theory and just took lambda to be negative, then you would get the same effect like in QCD, that the coupling gets strong at small scales. It's just there, it's unphysical, but here it's physical. Questions? So let me give some intuition for, this is sort of made up, some made up intuition for why this is the answer. Meaning the answer is that, so in the QED and QCD cases, there's intuition for why the beta function is positive in one case and negative in the other. So let's attempt something similar in this case. So in the positive coupling case, this is the defocusing case, so the waves repel. So the spatial distribution of the field is nearly uniform. On the other hand, in the focusing case, the distribution is highly inhomogeneous because there are collapses. So this is a picture from some paper illustrating the collapses. So there are different regions in space which are collapsing. And so if we switch to a particle language, we could say that low momentum particles are less likely than high momentum particles to escape these collapsing regions and therefore experience a stronger effective interaction, which could explain the curve that we see. Let me mention one last effect, and then I'll move on to the second part of the talk, the Keldysh contour.
So
Yes.
for negative lambda, the coupling doesn't grow to infinity with distance, it just kind of stabilizes.
For negative lambda, the coupling gets large as you go to low K.
Okay,
Just like in QCD.
okay.
And our interpretation of that is this happens because the low momentum particles have a harder time escaping collapsing regions, and so therefore experience a strong interaction because they're in the background that's collapsing, and so they interact strong. So the final effect I want to mention is this. So our N of K that we found in the positive lambda case, one thing I didn't mention before, it depends on the IR cutoff, the total wave action. And this is a novel feature. So usually in both Kolmogorov turbulence and weak wave turbulence, one says that it's independent of pumping and dissipation. So it doesn't matter, the pumping and dissipation scales are not supposed to enter as long as you're in some inertial region. That's not really true in Kolmogorov turbulence, but never mind. The effect that we find here is that N of K depends on the IR cutoff. And so this is abnormal because usually we're fine with getting anomalous exponents, like when we get anomalous exponents in dimensions of operators, but those are usually compensated by UV cutoffs, not IR cutoffs. So here we have an IR cutoff that enters rather than the UV cutoff. No one seems particularly, let me state this again for emphasis. So we're setting up an inverse cascade. So we pump in the UV and the cascade goes into the IR. It's the same direction as an RG flow. It's an inverse cascade, so it's just like an RG flow. We're starting from the UV and going to the IR. And the answer that we measure for N of K depends on the destination. So you're like at some K, and you don't know when the cascade is going to end, but the answer for N of K evidently does know because the IR cutoff enters. And that seems abnormal. Okay, so let me give a summary for the first part. So standard kinetic theory, is only valid for weakly interacting waves, so the Boltzmann equation and so on. So we extend it to strong interactions by writing a large N kinetic equation. And the main theoretical results are that for strong turbulence, we find independence of the flux and critical balance scaling for negative coupling, which has long been conjectured, but has never been shown in any dynamical equations. And so this is independent of the flux, so that's universal. And in the positive coupling case, it's independent of the answer for N of K is independent of the coupling, making it also universal. This critical balance scaling in the focusing case is likely related to collapses. And there are other cases which are more complicated than nonlinear Schrodinger, such as spin waves, which fits into this universality class of focusing nonlinear Schrodinger. So if you take spin waves and study wave turbulence there, we believe you get the same answer as the focusing nonlinear Schrodinger at strong nonlinearity. Okay, so that concludes that part. In the last 10 minutes, I just want to describe how we do the calculations and how they can be mapped into the language, the standard language of RG and field theory. There are no questions. Okay, so if you missed everything, you can pay attention now. So the standard statement of how we define field theories is that you define it on the UV, like on a lattice, and then you want to ask what the IR behavior is. This is like the condensed matter viewpoint because you want to know, and you want to know if you change the UV Lagrangian, if it affects the IR. And tree level RG gives the answer in a simple way. It's basically dimensional analysis. So if the operators are relevant, they change the answer, and if they're marginal, if they're irrelevant, they don't. And marginal interactions are borderline because you need loop corrections. And then the answer can be highly sensitive, like in QED or QCD. They're both marginal, but the loop corrections give completely different answers. So one thing to emphasize, which is well known, is that all of this analysis is state dependent. So the RG analysis we just discussed in the previous slide, that's state dependent, and the assumption was that you're in the vacuum. So one case in which this is not true is if you have a Fermi surface. So if you have a Fermi surface, as you do RG, you land on the Fermi surface, and now you can keep integrating out, but you're still going to stay on the Fermi surface. You don't shrink to the origin. And so interactions like psi bar psi squared, which in 4D and 3+1 are irrelevant, become marginal on the Fermi surface because the Fermi surface is effectively 2D. And in 2D, this is marginal. And so depending on the sign of the beta function, you either get superconductivity or gapless free fermions.
There's also an issue of renormalizability.
Yes.
Some theories could be non-renormalizable.
Yes.
What is that? Is yours?
What is that?
What is yours? What is weak turbulence? Is it renormalizable in the sense of
I don't
quantum
think,
field theory are renormalizable?
but from I don't think it matters. Why does it matter if it's renormalizable or not? We're just asking. Yeah.
If it's not renormalizable, then
But we only care about the IR.
the small scale dominates the physics at large.
If it's not. So the point of this slide was that the entire modern viewpoint of RG is that you don't care if it's renormalizable or not renormalizable. You just want to know what happens at low energies and how stable it is to changes. So. As long as we're doing inverse cascades, it's in the same direction as RG and it fits into that framework. Direct cascades are more challenging.
Wait, is that the viewpoint we take even for negative lambda?
Say again?
Is that the viewpoint we take even for negative?
Yeah, I was always doing inverse cascades. So let me just remind you, so why I said,
Negative means focusing states.
that's right, focusing, yeah, that's right, collapses, yeah. So let me just remind you why tree level RG is dimensional analysis, and then I'll extend it to general states. So if you take lambda phi to the fourth theory, the strength of the nonlinearity, by the same logic before, you just take the ratio of the nonlinear term to the linear term, you replace phi with the dimension of phi, d minus 2, and you get that this nonlinearity parameter is k to the d minus 4, which is the standard dimensional analysis. So if d is greater than 4, then epsilon k is going to 0 at small k, so it's irrelevant. And for d less than 4, it's relevant. So this analysis was near the vacuum. If we take a general state, so if you say, so it occurred near the vacuum when I did this replacement going from here to here. If I take a general state, then I should replace expectation value of phi squared with like nk plus a half over omega k. Phi is like a bosonic field, ak, expectation value ak dagger ak is nk. So that changes this line. So now I get this factor of nk plus a half over here. So if nk is 0, then you just have a half, and it's like that in the vacuum. But if nk is k to the minus gamma, like I've been taking, a much greater than 1, then this nonlinearity parameter is d minus 4 minus gamma. So if gamma is positive, which it usually is, that means if you had an interaction which was marginal in 4 space-time dimensions, it's now become relevant in this state. So if the interaction is relevant or irrelevant is a state-dependent question, and for interactions that are marginal in the vacuum, they can become relevant in these states. Good. So the whole goal can be succinctly said as our goal is to study RG flow for marginal operators in these states with nk going like k to the minus gamma. And we want to know if the beta function is positive or negative to establish if the interaction grows at small k or decays at small k. So the way one does the calculation is the standard Schwinger-Keldysh contour. So we need to compute the beta function, but in these states. And so we need to compute not in-out correlation functions, but in correlation functions, because it's an expectation value in the state. And so one can trick the path integral into producing that. An in correlation function as opposed to an in-out by having the contour go forward and backwards. So it's convenient to place a field, to call the field on the upper branch phi plus and the one on the lower branch phi minus. One then does a field rotation. This is all very well explained in Damson's paper. One does a field rotation, and then because one has two fields, one has multiple propagators. So the phi propagator is called the Keldysh propagator, and the phi eta one is the retarded Green's function. So Keldysh is basically just as easy or difficult as the vacuum. It's just there are two fields instead of one. And so if you look here at the phi, there's an nk here. I'm going to drop the 1 cap, and nk goes like k to the minus gamma. So as a result, that will affect the dimension I assign to phi. So I'm going to assign the dimension to phi, which is d minus gamma minus 2 over 2. So initially, it seems puzzling how. So I previously said that it's clear that RG and so on is state dependent, and it seems puzzling because we normally count dimensions of operators just from the Lagrangian to determine if it's relevant, irrelevant, and changing the state doesn't change the Lagrangian. And the way it enters is that you should read off the dimensions from the propagators, and this propagator, the phi one, knows about the state, and k enters here because when inverting the free part of this action, d eta d phi, you have to insert boundary conditions on the left half, which is how nk entered. So even though the Lagrangian doesn't have the state, it enters when you get the propagators. So now we do the standard Wilsonian RG procedure of computing the beta function in the state. So we integrate out a shell. We see how the effective action changes, and we produce the beta function. So the case that, like in QFT, the case that, so in QFT, we normally study cases in which the interaction is marginal. The reason being, if it's relevant, you just quickly lose perturbative control. And so what we did here was and so nonlinear Schrodinger, which I wrote previously, that the interaction is relevant, and so there's not much to say without like taking large N for the actual nonlinear Schrodinger. So what we did here is we just made up a Hamiltonian del squared psi squared plus lambda del squared psi to the fourth, so that the interaction is marginal in the Kolmogorov-Zaharoff weak turbulence state. Out of the 20 cases that are known for wave turbulence, I don't know of a single one where the interaction is marginal or even close to marginal, unfortunately. But in any case, since the interaction is marginal, the beta function is trivial to compute, and it looks like the naive answer you would expect, that it just goes like lambda squared. It's always the same thing. And so in this context, we can now answer the question of if the coupling gets stronger or weaker as you go into the IR. And qualitatively, the answer is the same as we got for nonlinear Schrodinger with large N. In the positive coupling case, the coupling decreases in the IR like in QED. So the interaction is marginally irrelevant, which means that NK actually becomes steeper than Kolmogorov-Zaharoff k to the minus gamma, and in negative coupling, the opposite happens. Yeah.
So you mentioned that for this Kolmogorov state, in this case, if this is specific action, the interaction is marginal.
Yes.
But in the general cases, what is it? Is it relevant?
Or irrelevant, yeah.
Okay. But you mentioned like out of the 20 cases that you know,
It's
there's no one.
it's not marginal in any of them.
Okay.
It's not marginal in any of them because the reason is because this exponent, the exponent that enters in the KZ state, it's d, the dimension, plus 2/3 beta, where beta is the scaling of the interaction, minus alpha over 3, where the dispersion relation is omega is k to the alpha over 3. And so you normally don't even produce an integer. So normally when we're counting, we get dimensions that are just well, they're still not integers. I don't know. It seems odd that none of them are marginal, but it's
And this second number square in the first line is a mistake, misprint.
where?
Second number square.
Second Nablus square. No, this is correct. I did mean Nablus squared to the fourth. Yeah, I really did mean that. It's not a mistake. Actually, let me back up. It's not hard for me to make an interaction that's marginal. I just made one up here.
Yeah.
It's just this.
Right.
No one studies this because I guess it doesn't describe anything.
Yeah, that was my question. Like in the cases where turbulence is describing known phenomena,
Yeah,
it tend to be like relevant.
it's usually irrelevant. Yeah, it's not marginal. One could try doing the epsilon expansion in some of the cases. But
But where is n here, or n is
but
number of species?
no, here I don't need large N.
No,
If the interaction is marginal, I don't need large N. I mean, we're still going to stay in weak coupling, but it's like QED. You can still get. It's like the problem is that the physical cases like nonlinear Schrodinger are like QED and 3D, and then you really can't do much. So that's why I need either marginal or large N.
Are you studying this in a box or I mean, doesn't this theory have unconstrained modes, zero modes that just grow? Like fractal, it attempts to do fractal field theory? Like attempts to do fractal field theories? This looks sort of similar pathologies, like where you have del squared acting on something.
Oh, I see.
So you'll have a linearly growing psi mode that sort of out of control.
I don't. Maybe that explains why this Hamiltonian is not realized in anything physical. Yeah, I mean, the extent of studying this theory was just I just used the fact that the interaction is this result is somewhat trivial. It's just with these, I just needed the scaling of the interaction. So the scaling exponent of the interaction is like 8 because 2 times 4, and the dispersion relation is 4, and so it satisfies what I need so that in this state you can check the interaction is marginal, and then it's just trivial. That the beta function goes like lambda squared, so that's the extent of the theoretical analysis. Yes,
So here, this is like, first of this could touch Hamiltonian, but this
Yes.
positive and negative coupling qualitatively matches
that's right.
the case where.
That's
it
right,
does
that's
not,
That's right. It's qualitatively the same answer that for positive coupling, it's like QED. For negative coupling, it's like QC.
But in that case, it's relevant. Yes.
It's in that case, it's
If the lambda is relevant. in that
that's
case.
right. That's right. That's right. Okay, so that concludes my talk. There'll be a program at the Simon Center discussing the long-awaited revival of applications of quantum field theory to wave turbulence, which allows progress from weak to strong turbulence in analytic theory, which happens to coincide with what I talked about for some reason. All right, okay.
Could you summarize what you think are the kind of most still open problems here?
Almost all of them are still open.
Well,
Open problems for wave turbulence.
no. Ideally, what's your dream? What are you hoping to accomplish?
So given any interaction, to just be able to tell you how NK is in the strong turbulence region. So just categorizing the universality classes. So like take surface gravity waves in the ocean, the interaction is some horrible mess. It's not like nonlinear Schrodinger, and I just want to know what NK looks like at strong nonlinearity. And so one could imagine some sort of RG-like argument where you just say this is the interaction, but these are the symmetries, this is what it flows to in the IR, so this will be the answer for NK.
When you say what it flows to in the IR, what kind of answer are you expecting in that kind of?
So for example, for spin waves, the interaction is like nonlinear Schrodinger, but with some derivatives. And so so from an RG viewpoint, it seems reasonable that as you go into the IR, you generate the nonlinear Schrodinger term, which dominates in the IR. And so from that perspective, you would say whatever I said the answer is for NFK for nonlinear Schrodinger will be the same answer for spin waves. So that's what we got out of log n, but we haven't done numerics, so that may or may not be true. So that's the flavor of the answer. Yeah, the question is just finding what strong wave turbulence looks like. The state.
But is there an underlying field theoretic structure to the infrared fixed point? In the vacuum state, we know that the answer to that question is something like a conformal field theory. And we know that there's an enhancement of symmetry and extra mathematical structure, and we know what it means precisely to characterize universality classes. Is there something like that you have in mind? I'm trying to understand when you say you're trying to figure out the infrared universality class, what shape does the answer take? Is it more than one exponent?
Yeah, so for positive and negative, so the thing that wasn't obvious in what I said for spin waves, you could say, okay, in the IR, it's just like nonlinear Schrodinger because the derivatives go away. So but from that argument, you won't really know if you're going to get the case of positive coupling or negative coupling. And the answer turns out to be the negative coupling case, which physically is related to the fact that spin waves also have collapse events. So I think my answer was formulated in a practical way, since most of the people who work on turbulence-related things don't know anything you're talking about. They just care, like they have some equations for some plasma. They just want to know what NK looks like. And so the goal is to find how to get that answer.
For example, do people care about like various kinds of correlation functions in the steady state, or is it only sort of as far as you only care about NK?
Yeah, so once you get NFK, then you can ask about correlation, then you can ask about higher moments in the state. So ideally you would want the whole, so we can rephrase it in a different way. So there's, so if you're in a thermal state, sort of without doing anything, you know the entire density matrix and probability distribution is just e to the minus beta h. And so any correlation function in thermal state, you know, because you know the full density matrix. So now we're asking in a wave turbulence state, what's the analog of that? So what's the probability distribution of the field? Once you have the probability distribution, you can calculate all correlation functions. And this is the approach for finding that probability distribution, is first finding the second moment and then perturbatively getting the other ones.
And the definition of wave turbulence state in that sentence was what?
Just means, instead of, so when you're doing the thermal state, you have a closed box. So you have a closed box, you say at late times it's the thermal state, you have to just, now I just change the boundary conditions. So there's pumping and then there's dissipation, and now I just ask what's the density matrix for the field psi. So once you relax this insistence that's always made on closed systems, it generates, it's like the same exact questions as statistical mechanics, but now with an open system as opposed to a closed one. And most systems are open anyway, so. And ones that are closed at intermediate times, they look open. Like in the heavy ion collision, you start with a far from equilibrium state. There's a large window of time in which there's just a cascade. It looks very similar to as if you had pumping, even though it was just an initial state that was far from equilibrium, and then eventually thermalizes, but over this long range of intermediate times, it's like it's an open system. Yes?
Could you just say again why large n worked in this case?
Oh, y agrees with n equals one?
Yeah,
I don't know.
so it's basically experimental. You
Yeah.
large n analytically, you see that it's pretty far.
Yeah, I don't know. It worked both. So in the focusing case where we get the critical balance spectrum, one could have said critical balance is a fairly, so in fact, phrased in field theory language, what's happening with critical balance scaling is, so we're starting with nonlinear Schrodinger, the operator is relevant in the, we start off in the UV, it's the relevant interaction in the state. Then you keep flowing into the IR, and the state adjusts itself in such a way that the interaction becomes marginal. That's what critical balance means, because the nonlinearity becomes a constant. So you're doing RG flow, and along the RG flow, the state changes so that the interaction becomes marginal, which is sort of interesting. So that one could imagine and hope that there's some explanation for why this is generic, which would explain why large n matches n equals 1. The defocusing, the case of positive lambda, I'm not sure. It may not really match exactly because, like, so if you look at the numerics, so this line is 8/3. So this curve is consistent with 8/3, but it would have been consistent with 8.5 over 3/2. So, so it's really the focusing case that we expect to be more robust. It would be nice if there was some argument, some RG style argument for it. One complication is, unlike normally field theory, you pick the state, then you start computing correlation functions in the state. But in the way we do the calculation, we don't know the state. So we assume the state is stationary, then I compute Schwinger-Keldysh on the state, then I get a kinetic equation, then I solve the kinetic equation to get a stationary state and say, okay, that was actually the state that you needed to take all along. So it's like a highly nonlinear loop-like problem. Yes.
So in terms of open questions, this is all for the reverse cascade.
Inverse cascade, that's right.
So if in the kind of other case, are there like, you expect similar methods? Yeah, or
The next thing we should do is direct cascade. For large n, that's reasonable because for large n, we have analytic control over all scales. We didn't do direct cascade. If the reason we did inverse is because we want to be pumping in the region in which the nonlinearity is weak, so that at least you have perturbative control there. But if you're doing large n, then you should be able to do direct and inverse. The direct cascade is also strange in that
It's the opposite to it's the other way around, how you normally think about RG.
yeah, so inverse is like the direction of RG, direct is the opposite direction. And so like there are many papers from the 70s and 80s when people are doing Navier-Stokes, which is direct except in 2D. And so then they keep pointing out that it looks very different. Another way of seeing that it looks different, in the same way in which I was computing dimensions of operators in this KZ state, because n of k goes like k to the minus gamma, which is influencing the dimensions, if it's a direct cascade, then higher operators with more fields, they become more and more relevant. And so this is another, so direct cascades are really puzzling from that viewpoint, because from the interaction yourself that you're looking at, it may be coming, it may be going one way, but then the higher, so it's no longer a given that interactions with the terms in the Lagrangian with many fields are irrelevant. They could become relevant in this state.
Educational question. So Navier-Stokes fluid in 2 dimensions shows inverse cascade.
Yes.
And weak wave turbulence?
Weak wave turbulence always has, if it's a quartic contraction, there's always two cascades. The reason is because if it's a quartic contraction, the wave action or the total wave number is conserved just because 2 to 2 interactions. And so that's why there's an inverse cascade. If it was 2 to 1, if it was just a cubic wave interaction, there would be no inverse cascade, it would only be the direct energy cascade. So it's different
It's
from
not
2D.
related to dimension. For weak turbulence, it's for wave
No.
turbulence.
Dimension does not enter in wave turbulence, as long as it's greater than
Yes,
1.
and for fluid, it does.
Yeah, that's right. Because fluids, it's related to vorticity and so on. Here, it just doesn't matter. It's because the KZ, the Kolmogorov-Zahara state, the exponent always has a D. And then the physical quantity is nk k to the D, so the D just drops out of everything. So perhaps restated differently. So normally in field theory, you get a marginal interaction, or epsilon is like 4 minus D. That's what controls. Here, it's not the dimension that controls, not the space-time dimension which controls if the interaction is marginal or relevant, but the scalings of the interaction and the dispersion relation. So that's why I could tune the interaction dispersion relation to make it marginal.
Okay, if there are no more questions, let's thank our speaker again.
It's used in general, you are
In back example from, yeah. That's it, right.